In this module, we are going to focus on primes and some of their properties. A lot of the things in this module would be something you have already seen. So I will be going a little faster than normal, but if there is some property that you are not aware of, it would be good to sort of review that property here. A number p greater than 1 is called a prime if the only positive factors it has are 1 and p, no other positive factors that will make it a prime. A positive integer that is greater than 1 and is not a prime is called composite. Note that 1 is neither a prime nor a composite. So here are some examples of primes, 2, 3, 5, 7, 11, etc. There are people who focus on finding larger and larger primes. So the largest prime that we have, there is a Wikipedia page that you can look up to find the largest primes that have been found so far. At the end of this module, we will actually show that the number of primes is infinite, so there is no such thing as the largest prime as such. It's the largest prime that we have found so far. So we're going to go through some properties of prime numbers. So the first property that we have is if I have a positive integer n greater than 1, it has a prime factor that is smaller. Now we can do this recursively. If n itself is not a prime, then it is composite. That means it has factors, and we can ask the same question about the factors, and if that factor is a prime, we are done. If that factor is not a prime, we find its factors and so on and so forth. If n is composite, then it has a prime factor that is less than or equal to square root of n. The proof of this is fairly straightforward. It's a proof by contradiction, which says if n has two factors, let's say a and b, and both of them happen to be greater than square root of n, that would mean that the product would be greater than n, which is not the case. A corollary of this, which is the contrapositive, is if I don't find a factor up to square root of n, then I know that the number is prime. There is a conjecture that every even integer greater than 2 can be written as sum of two primes. It is one of those conjectures that have been tried for larger and larger even numbers, and we have found it to be true, but it hasn't been proved as of now. The fundamental theorem of arithmetic says that every integer n greater than 1 can be written uniquely as a product of primes. So for example, if I have 3960, I can factor it into 222, 33511, and so we can write it as 2 to the power 3, 3 to the power 2, 5 times 11. The proof basically is something like this. First, we have the existence of prime factorization. This comes from the theorem we had earlier that says there is a factor that is smaller than or equal to n. There is a prime factor smaller than n. So we can take that prime factor and then divide the number by that prime factor. We will get a smaller number, continue until we get all the prime factors. The next part is showing that we can't have two different prime factorizations. And essentially, to do that, what we're going to do is we're going to look at the two prime factorizations, cancel out the common terms. Now we are left with two expressions. Let's call that S and R, which do not share any common prime factors, but their product is the same number. Now that is not possible because of the property that we have, that is prime numbers don't have any other factors. Here is a algorithm for finding factors of a prime. Again, I'm going to describe the algorithm, but it's not a very efficient algorithm. So essentially what we're going to do is we're going to start with the given number n, and then we're going to start with all the primes that we have, starting with 2, 3, 5 up to square root of n. If any of them is a factor of n, then n is not a prime. And so once we find the factor p, we divide n by p. Note that we have found p to be a factor of n. That means that we have n over p is going to be integer, and that means that we can start finding factors of n divided by p, and when we find those factors we will have all the factors of n. To do this, we need to know the list of primes, and the way we can go about doing this is as follows. So let's try to find all primes less than or equal to 100. So first thing we can observe is if a number less than 100 has a factor, then it must have a factor less than or equal to 10. We got this because we know that if I have a number n, then it has a factor at least, it has a factor that is less than or equal to square root of n. So the factors less than 10 are 2, 3, 5, 7. Then what we're going to do is eliminate all multiples of 2, 3, 5, and 7. Now what is left will be all prime numbers less than or equal to 100. And these prime numbers are given here. It would be a good idea to be aware of all prime numbers less than 100. Just will make stuff a lot easier going along. Now, if I have factors up to 100, we can use the same idea to find all primes up to 10,000. Because if a number less than 10,000 has a factor, it must have a factor less than 100. That means it must have a factor from this list. Here is another property of primes that I want to look at, that there are infinitely many primes. The way we can prove this as follows. Now, one question that we discussed at the beginning of proposition logic or proof methods is which method should I use for proving, direct, indirect, etc. Now in this case, we're going to do proof by contradiction because we don't really have any hypothesis. Hypothesis basically means that something that is given to us, we don't have that. We have a conclusion that says that there are infinitely many primes. So if I do proof by contradiction, I will get one more premise, which is that the number of primes is finite. So we're going to do proof by contradiction as follows. Let's say we have only a finite number of primes. That means there is the largest prime. So in this case, let's say that largest prime happens to be p. Then we can compute the number n to be p factorial plus 1. P factorial is 1 times 2 times 3 times 4 up to p plus 1. Now, based on the theorem that we studied earlier, that n must have some factor that is a prime. Well, the problem is n cannot have a factor less than or equal to p, and the reason is basically straightforward. If I divide n by p, and remember n is something like this, so if I divide n by any number less than p, I'm going to get the remainder of 1, and that's because this number without the plus 1 is always going to be a multiple of a number less than p. But that means that n has to have a prime factor that is greater than p, but we had assumed that there are no primes greater than p, which is a contradiction, and that means that there must be infinitely many primes. It turns out that not only there are infinitely many primes, there are quite a bit of number of primes. So if we denote pi of x to be a number of primes that are less than or equal to x, then what we know is pi of x is roughly equal to x divided by ln of x. We're not going to get into the proof of this. The proof is fairly complicated, but we can observe this with different values of x. So for example, here we have x going from 1000, 10,000, etc. And pi of x is the number of primes that are less than or equal to x. And this is the value of x divided by ln of x. Now, if you observe, these numbers are, if you take the ratio of these numbers, they're getting quite close to each other. And that's sort of a validation we can use, that the number of primes that we have less than or equal to x is about x divided by ln of x. We have reached the end of the module, so go ahead and please do the review quiz. The review quiz should be fairly straightforward, as in this module we talked about stuff that most of it you should have seen before, except possibly the proof of the fact that there are infinitely many primes. Everything else you would have probably seen before.